My name's Matt Roughan. I'm from the University of Adelaide and ACEMS, and I'm going to be talking today about traffic matrices, as you can probably guess from my brilliant title slide. Just a few words of housekeeping to start up. This is all pretty new to me, this way of presenting. I've been doing it a little bit with classes, but I don't think I'm terribly good at it yet. So partly what I'm doing today for my own sake is learning about how to do this a little bit better. So I'm trying to do a talk that's actually a variant of a talk I've given before, and some of you may have even seen some variant of it. But hopefully the presentation style at least will be different enough today that this maybe seems a little bit new to you. And I'm not going to try and do anything too advanced mathematically. I'm going to keep it pretty simple so that we can just sort of play around with slides and drawings and so on. So we'll just see how that goes. So let's get started. So this is really kind of a story where I hope I'm going to introduce myself a little bit. I guess one of the questions Sarah sent out at the start was, should I get someone to introduce me before we all get going? But I think the talk in my head is meant to give you a little bit of a view into my life as a researcher. I did my PhD in Adelaide, so I'm back at Adelaide now, but I did my PhD in applied maths at Adelaide on queuing theory. And back in those days, queuing theory was mainly, or at least the work that I was doing, was mainly oriented towards telecoms and solving problems to help telephone operators. But I was working on some pretty theoretical problems, and I had really no idea about data. I had no conception of how I would map my work to a real problem, but I still somehow imagined that would happen. I felt like I was doing this theoretical work and some lovely person would come along and take that and map their data, and then it would all be useful. That was a little bit naive, shall we say. After my PhD, I went to CSIP, which was the Cooperative Research Centre for Sensor Signal and Information Processing. And then I actually got to learn a bit about data. And I went through a series of jobs culminating at AT&T, which is one of the biggest telecoms providers in the world, working on their new, or what was to them relatively new, internet at the time. And I still, all the way through this, even though I'd been learning about data and learning more and more about how to work with data, I still had imagined this queuing theory stuff that I'd been doing in mathematics. When I got to AT&T, finally I would meet up with the people who were going to take my theory, which was, I thought, really cool, and map it to the real network, and suddenly we would have this glorious point of contact. Still naive. Got to AT&T, no one was interested. They weren't interested, not because they thought what I was doing was particularly stupid, but it was 5 steps removed from what they could actually see. So let me explain what I mean by that. I was, the particular bit I'm thinking of at the moment was work on long-range dependence in traffic source similarity in traffic, which is a very cool topic. It's very interesting. But it's like a third order effect. And they didn't even really have a good way of estimating the averages that they needed to estimate, let alone variances, let alone some sort of third order effect on the traffic. So I credit myself with being smart enough to shut up and listen for a little while and find out what their real problems were and try and listen to the operators and solve problems that they actually cared about. And one of those problems was that in order to optimize a network, and this is a classic optimization problem, network optimization, you need an input which is called a traffic matrix. And there's probably 600 papers written about this optimization problem, maybe 1,000 papers written about network optimizations, and every one of them starts with this just subtext of, and God gives me a traffic It's just assumed to be something that's easy to measure. It's assumed to be something that you just get. And in fact, it's never been something that's easy to get in the telecoms sector. There's work on estimating and measuring them for telephone networks going back to the 30s. And we started trying to do it in the internet and found exactly the same sorts of problems. So I want to talk about this problem of traffic matrices. I'm going to tell you what a traffic matrix is in detail as we go along. But perhaps we can start with a problem, an estimation problem that's conceptually a little bit easier. So let me tell you about network tomography. Let's start with this, tomography. So if you've ever heard of CAT scan, the T in the CAT scan is for tomography. Let me try and draw a picture for you, but excuse my drawing skills because I really am not an artist. So let's assume a person here. God, that's a pretty bad person, but I said excuse my art skills. So let's put that person's head. Actually, we probably want to leave the head attached to a body, but I'm not going to even try and draw a body. Let's put that head inside some sort of machine, which has an emitter over here and a sensor over here, and we'll put a bunch of rays through. I don't care what those rays are. They could be X-rays, or they could be some sort of positron emission ray thing, or there could be some sort of magnetic resonance thing. I don't understand the physics of all of these things, but what you do is you send some sort of measurement through the head, and then if you just did that, you'd get kind of a cross section. So you get kind of a cut through, and that's where this tomo comes from. But what you do is you rotate and you take other cuts through. And the goal then is to reconstruct a 3D image of someone's brain, usually, from this series of cuts going through their head. We have an analogous problem in a network. So let me draw you a junior GWiz network. I would call these things routers or switches. And graph theorists might call these edges, but I'm going to call them links. And they might be fiber optic cables, or they might be actually some sort of virtual link that doesn't really exist physically, but is made up of some sort of logical protocol exchanging packets over some more complicated underlying infrastructure. We care about managing a network like this. We care about what's happening in that network. And one of the common problems that you have in a network like this is a link can become congested. So you can imagine lots of people want to use this, and there's too much traffic to fit in the capacity, so you just get packets. In fact, I should say something about the internet. The internet is what we call a best effort network, which means that if you have too much traffic, it just drops it. So that might sound incredible to you, but the internet does not regard your traffic as valuable. So if there's too much, if it fills up the queues, the buffers, then that traffic will just get dropped on the floor, it will get lost. You can recover from that by retransmitting, but that slows you down. So in fact, we at the start of this had a little bit of a discussion about crappy internets and the fact that I'm on a pretty crappy internet connection here, and lots of other people have had trouble with Zoom over the last nearly month because we've swapped to this online teaching mode, and so there's this huge capacity drain on the internet. So there's lots of congestion happening at the moment. Network operators don't want that to happen. They don't want their customers to have a bad experience, so they would like to find places where congestion is happening. But it turns out that it's much harder to do than you might naively think. You might naively think that whoever sold you these routers sold you some way of measuring what was happening on them. And indeed, various companies have done that, but usually those measurements are so unbelievably bad that they're completely untrustworthy. How do you get around that? Well, imagine that I have a computer over here, laptop over here, and a laptop over here, and they're connected up to this network. Then I can send packets, I can send data between them. So I could send a probe packet like this, and I could measure the latency. Latency is what we call delay in the internet. I could measure the delay of that packet going from point A to point B. That seems simple enough. I could do a lot of those. I could do probes around here, and I could do probes around here, but this doesn't scale. If you have n routers or n locations or n points of presence in your network, then there's going to be order n squared paths through this network, and n might be on the order of thousands. It might actually be on the order of tens or even hundreds of thousands. You don't want your probe traffic itself to become the thing that's causing the congestion. You want to send probes relatively often because you want to spot congestion as soon as it happens. But if you send them too often, and if you send them from too many different locations and too many different paths, then you will overload the network just with the measurement traffic. And that would just be crazy. That would be ridiculous. So what do? Well, we choose a subset of paths and we carefully design our probe strategy. Carefully. In fact, what tends to happen is people probe where they have available infrastructure to set it up. But let's assume it was careful. We send some probes through here and we work out one little trick, which is that imagine I measured the delays of packets across, this is link 1, this is link 2, then the traffic, call this Y1, the delay Y1 will be X1 plus X2. Obviously, this is, you're measuring an underlying stochastic system, so these will be estimates. They might be based on multiple measurements. You might be doing some sort of clever estimator on top of this, given some sort of prior distribution of delays and so on. But just for the moment, let's assume that these were just numbers and the delays across a path is just going to be the sum of the delays on the components of that path. We can do this over a set. So let's make this Y2, and this is going over links X3 and, let's make it more clear, X2. Right, let me do it in a different color. So let me make this Y2, then Y2 is equal to X3 plus X2. Now, I can take a whole lot of those measurements and I can rewrite this in vector form as Y equal to AX. These are my measurements. They're path measurements. The X's are the thing I want to know. And why would I want to know that? Well, if one of these X's becomes large, if the delay on that path becomes large, that's significant. That tells me that there's some sort of build up in the queues, and therefore there's some congestion on that. So measuring these X's would tell me where congestion is in my network. What's this A? Well, A is we have ones here implicitly and zeros on all of the other coefficients. So this is a 0-1 matrix, and we traditionally would call this an incidence matrix. And it's just a matrix which has ones and zeros, or one indicates that a particular link is used on a particular path. It has a special name in my context. It gets called a routing matrix. why call it a routing matrix and not an incidence matrix? Well, it's almost history. It's almost that people who started this didn't know what an incidence matrix was, so they just came up with a new name. So now we have a set of equations. We need to go and solve them. The naive, again, way you might want to solve them is just multiply by the inverse matrix. And this will give you an estimate of x. But of course, this is not even a square matrix. The number of paths is not necessarily the same as the number of edges. It's not necessarily a invertible matrix, even in the cases where it's square. And so you can't just perform this. However, it's a standard estimation problem to take systems of equations like this and try and invert. It's called a linear inverse problem, and there are many examples of it. I'm going to give you another example of a linear inverse problem in just a second, and I'm going to show you a very general strategy for solving those sorts of problems. So I'm now looking at my picture on the screen, and it's a horrible, horrible mess. Does it make sense to anyone? You're welcome to ask questions at any point during this talk. I'm going quite quickly through what I was planning, so we may not be going for a full hour here. Well, look, thumbs up. That's brilliant. Love that. Let's go on to the next bit. Actually, I don't want to talk about traffic matrices just yet. I want to talk about SNMP. So when I joined AT&T, the sort of measurements you could actually make in most networks were not what I imagined. When I imagined making network measurements, in fact, I'd actually done this back in my postdoc in Melbourne. What you do is you have some sort of fiber optic cable, and you put what we call a splitter into that cable. This is a very simple device. This is a fiber optic cable, so this is just an optical device called a Bragg grating. And what it does is, if your light is going in this direction, it will split off, say 10% of the light, and you send that into the computer, which just records it. So what you can do this way is make a direct recording of all the traffic on a link. But as you can imagine, this is a lot of data. You think about the internet today, even when I joined AT&T, a typical link in the internet was something like 10 gigabit per second, and now they're much faster. 10 gigabits per second means you would be downloading 10 gigabits a second to your laptop, and most computers can't even cope with reading data that quickly. So this is a classic big data problem of people described it as trying to drink from a fire hose. Just have data coming at you too quickly to do anything with it. You need to have some strategy for working with that. And we were playing with many ideas in this sort of space. But the other problem with this is when you go to a network engineer and tell them that you want to put a splitter into the network, they get kind of grumpy. Why would they get kind of grumpy? Well, how do I put this splitter how do I actually do this? Well, the first thing I have to do is take a pair of scissors and cut that fiber optic cable. In fact, I wouldn't do it with scissors, to be honest, but you have to cut the cable. Network engineers are utterly paranoid about their cables. They lavish love and attention on their cables in a way that probably makes their lives a bit uncomfortable. They will not let you do this unless you have, perhaps if the CIA turn up at your door and tell them that you have to install one of these things, then they do it, but otherwise they're not going to. How do you measure networks? Well, there's a thing called the Simple Network Management Protocol. And I would really like to just remove management and call it measurement. it's actually probably what it gets used for more than management is measurement. And the brilliant thing about the simple network management protocol is it's almost ubiquitously implemented in almost every network device you're ever likely to come across. So if you tear your home router, your little DSL router or your NBN router or whatever you have at home apart, you'd probably find that it can do this. But what can it actually do? What it actually does is keep a little counter, and the counter is like an odometer in your car. It measures the number of packets or the number of bytes going across the link, and it just counts. And it counts up and up and up and up. And when it wraps around, it goes back to zero, just like an odometer in your car, and goes up and up and up and up. I can ask the router or the switch what number it's got at any given time. And so the way we use this as a measurement protocol is we send probes to each device in the network, and we send them every, say, 5 minutes, and just ask for the value of that odometer. This has so many problems. I've literally given entire seminars just on the problems in SNMP measurements. I can just talk about this ad nauseum because I spent so much of my life dealing with it. But anyone out there who's dealt with data, I'm sure you will be familiar with many of the issues that you see in SNMP data. Missing data, it's endemic. And because these are just odometer readings, they don't come with a timestamp. So if you have a missing measurement, you have to infer that it's missing from the lack of a data point. They have noise in them. They have just errors because this is a flaky little bit of software that someone wrote in their lunchtime. It's not like the main bit of software on the router. They have artifacts. They have crazy artifacts. So one of the things that's a big problem is that if you restart a router, it doesn't have hard memory. It doesn't keep all of these counters. They just get reset to zero. So you might think routers don't get restarted very often, so that's hopefully not a big problem. But actually, there are things called soft resets where some little bit of software within the router dies and gets restarted, and then you get counters being reset. So sometimes the odometer will just suddenly drop back to zero. So you get these crazy artifacts in it. SNMP is a horrible, horrible data source. The thing that's most pertinent for me, though, is all it does is count, and it tells you nothing about what's in the traffic or where it's going. So let me tell you about a traffic matrix. Again, let me draw a pretty boring little network for you. Let's give a few labels to these guys. What I really want, what I really need if I'm going to try and optimize my network, that is work out the optimal capacities for the links, or work out whether it's cost effective, for instance, to put a new link across between A and B. What I really need to know is a traffic matrix. So a traffic matrix is a big matrix of elements like this, TAA, TAB, and so on, where TAB is just this traffic flow. It's the traffic flowing into A and out from B. You might assume that the diagonal elements of this are zeros. So you might think that you don't get too much traffic that does that, flow into D and flow straight out from D. But this is an abstraction of a network. And sometimes those nodes aren't just a simple router. Sometimes they actually represent a whole network in their own right. And so that network can have traffic flowing internally within it. So you can have diagonal elements that are non-zero in this traffic matrix. It sounds like such a simple thing, and I think people doing optimization, to do them credit, it doesn't look like it should be a difficult thing to measure. In fact, if I were going to design network equipment, of course, I would design network equipment so it measured this automatically, because but the people designing real routers, they care about making sure packets do this. And they do it really, really quickly. And a lot of packets do that. So on one of these routers, there's literally maybe 100 billion packets flowing through it every second, maybe more. These things have to be really, really good at forwarding packets. And the measurements, the bits like that, they kind of get bolted on afterwards. So SNMP won't tell me this thing that I want to know, TAB. Let's do another one here. So TFD. What SNMP will do though, SNMP will tell me how much traffic is on here. So let's call this, and I'm going to reverse my notation here. Y is now going to talk to traffic on links. And I'm just going to call this, for the purposes of argument here, X1. And I could perhaps imagine traffic going through here and traffic going around here. And I'm going to give each one of those a label, an X. And one of the things you might quickly see is that if I zoom in on this link, then the traffic on that link will be made up of all of the traffic that's routed across that link. So I'll end up with an equation that looks like Y2 equals, in this case, X1 plus X3. Look familiar? It should look familiar because I deliberately set this up so I get equations that look really similar to the ones I had before. In fact, I'm going to write this out like this. These are my link measurements this time. The Y's are my link measurements, and the X's are the traffic matrix elements. But obviously I've written them as a vector this time. Okay, so they're not in a matrix form here. I can extend this over time, so I think of this as Y1 or Yi, and this is Xi, and then I could write big Y, A transpose X, and I could look at this as a spatiotemporal problem as well, and that's really interesting. But let's stay away from that one because it's a little bit scary and just focus on this simple problem. A is, once again, an incidence matrix. The really cool thing about this is that I've written this as A transpose. That's deliberate because A transpose is the transpose of, let me get my pen back. So transpose of this A that we talked about in the network tomography problem. And in fact, both of these problems originally were called network tomography because they're both the same type of problem. They have exactly the same structure. They use the same incidence matrix, just one is the transpose of the other one. And here we have path measurements. So if you have n paths, this will be a length n vector. If you have n edges, this will be length n, whereas this way round, y will be length n, and x will be length n. So once again, we have a linear inverse problem. We know y, we want to infer x. And when I was talking about that before, I kind of deferred the question of how you would go about solving that inverse problem, but now I want to address it just a little bit. So let me write it out again. It looks so simple, but really there's noise here as well. Remember I said this is, we're collecting these guys, these Ys from SNMP data. And this is a crappy data source. It's got noise, it's got missing data, it's got all sorts of crud in it. So we model that as some sort of noise term. This matrix, well, imagine the original network tomography problem. I said that we carefully designed that problem to be solvable? Well, you know, in real life, it doesn't get carefully designed. But now, in the problem that we're looking at now, we can't design it. This is a matrix that we are given by the network operators. We have no control over what this thing looks like. And it's horrible. This problem, if you think about it, we've got some number of unknowns, and we've got some number of measurements. This number of unknowns is usually way bigger than the number of measurements. This matrix is very not square, so we would call that an under-constrained problem. So let me put some numbers on here, actually. So in one of the original problems, and we did a lot of work to reduce the scale of this so that it was a bit more doable, but in one of the original problems, we had something, let me just try and remember, it was the order 10,000 unknowns and order 1,000 measurements. So that just gives you an idea of the scale of the problem. It's not like you have 1,001 unknowns and 1,000 measurements. It's just way out of whack. It's under constrained, but it can also be inconsistent. A real problem, you know, typically when we present first year mathematics and linear algebra, we talk about inconsistent equations where there's no solution, and we talk about under-constrained equations where there's an infinite number of solutions. But you can actually have both at once. You can have a system which has no solutions, but it's still under-constrained in the sense that there's more unknowns than measurements. This is kind of crazy. It can be ill-conditioned. What does ill-conditioned mean? Well, it means essentially that naive ways of trying to solve this are sensitive to small errors. And remember these errors we have here. If we have small errors and they feed into the solution in some way and get amplified, that would be really bad. So we have to deal with all of these things together, and that's kind of ugly. There is a standard toolkit, I would call it, for solving problems like this, linear inverse problems. What we do is we phrase it as an optimization problem. So x hat is going to be my estimate. We say it's the argmin. That's just, it's the x that leads to the minimum value. So it's a fancy way of saying find the best x. So this is a condition which comes from the measurement. So this is directly trying to make those equations equal, but we don't insist that they be exactly equal. We don't insist that they be exactly, we don't insist that this equality here be exact, because there can be inconsistencies in here. And if we tried to make it exact, we would end up with this sort of ill conditioning, this sensitivity biting us in the arse. So we have to phrase it in this nice way. What do these twos mean? Well, we're using the L2 norm here, the square of the L2 norm, in fact. Why the L2 norm of this? Well, actually, you could do different things here. You could use an L1 norm or even an L0 norm. You'd be solving a different problem. And L2 seems to work quite well for this particular traffic matrix problem. But I'm not wedded to it. In other traffic matrix problems where we've been doing things like detecting anomalies in traffic, we've actually used an L0 norm, and there's some great maths around doing those. But for the moment, let's use an L2 norm. We have to add another bit to this, and the other bit is because we have this under constrained nature of the problem. So it's actually an infinite space of solutions out there. If we just solve this problem that I've given you at the moment, we'd just be doing least squares regression. That's all this will give us. You know how to do that. It's easy, but it makes no sense here. And why does it make no sense? Well, least squares regression, underlying it is a kind of assumption of Gaussianity. In fact, if these variables were Gaussian, then this would be an optimal thing to do. So the underlying assumption is that the variables look, maybe something like this. Oh my God, well, it didn't appear to you, which is good because it's probably the worst Gaussian that I've ever drawn. Let me just have one more go at drawing a Gaussian. I haven't done this on my iPad before. It's a bit trickier with a kind of, that's not so bad. So that's my Gaussian distribution. Real traffic matrices look nothing like that. For instance, real traffic matrices can't have negative values. You can't have negative traffic. Real traffic matrices look much more, and I'm going to draw this as if they're on the same scale, but they're going to look much more like this. Very heavy-tailed distributions that these things come from. So least squares solution to this is really not that helpful. It also presumes we know nothing about traffic matrices. So actually we have quite a lot of knowledge about what a traffic matrix must look like. And we could phrase this as a bunch of axioms, or we could frame it in terms of some constraints in this problem. But actually an easy way to think about it is a prior model. Now, when I say prior, I don't necessarily mean, I know there's a lot of Bayesians out there, particularly computational Bayesians, but I don't necessarily strictly mean a Bayesian prior distribution. I just mean a model that we start with before we do our estimate. It could be a Bayesian prior. We can actually rewrite this to all be Bayesian, but I'm thinking a little bit more generally here. And we're going to add in a term to pull us towards that prior. It looks something like this, where this is our, call it prior model, although again, I don't want to give you the mistaken impression that we're necessarily doing Bayes here. This is a distance, or actually the one that we use, or the one that we found to be best, was the Kullback-Leibler. And it's not a distance, it's a sort of dissimilarity or a divergence. It's not a distance because it's not symmetric, but symmetry isn't what we need here. We need something that has some of the other metric properties like the triangle inequality. Let's call it a distance just for the sake of English language, because it gets really complicated if I have to keep just correcting myself and saying divergence. We also have a parameter lambda here. I'm going to talk about lambda in just a second, but this general strategy is called regularization. And it's a really powerful strategy. It's used all over the place. I was talking to machine learning people literally yesterday, and the first thing out of the guy's mouth when he looked at the problem that my student was looking at is we'll need to do some form of regularization on that. Different people have different ways mathematically of describing it or implementing it, but I think of it in terms of optimizations like this. The model that you choose is important. If you choose a better model, this will work better. But actually, even if you choose a bad model, this can have some good results. And that's really counterintuitive. But there's a lot of interesting work out there about regularization. It's really performing a kind of bias variance trade-off. And you're allowing a little bit of model bias. You're biasing towards some model that maybe is a little bit crappy in exchange for hopefully a dramatic reduction in variance. So lambda, how would we choose lambda? How would we choose lambda? Well, again, a little bit of knowledge about your problem is really important here. If I think my errors are small, if I think these measurements are really accurate, I want to emphasize this part of the problem. And so in that case, I would choose lambda small. And that would mean the distance component would be very small, it would have little influence, and I would be focusing on getting these equations from it. If, on the other hand, I think there's a really big error term in here, then I want to emphasize the distance, I want to emphasize the prior, because I'm a bit worried about my data. I hope that my prior will do more regularization. And in that case, I want to have lambda being big. So there's a clear problem that choosing lambda could be an issue if you don't know how big your errors are a priori. One of the nice things in the traffic matrix problem was we showed that if you looked at this for, say, values of lambda, in fact, this is log lambda, you see a curve that looks sort of like this. And that means there is an optimum value of lambda for our particular problem, but there's a really wide range of lambda values for which it works really well. We did this with traffic matrices. The model that we were using is what we call a generalized gravity model. I'm not going to get into all the details of that today. It doesn't really matter for you. But it isn't a terribly complicated model. It's the sort of thing that telecoms engineers might reach for first in their bag of tricks. And we found that this worked well enough for government work. In fact, well enough for AT&T's work. In fact, errors were around, I'm trying to remember off the top of my head, but around average 12% RMS error, which certainly good enough for optimization if you are careful about the sort of optimization you do. And again, you need, when you're doing optimization with results like this, you need to be doing robust optimization. That's optimization that itself is not sensitive to the errors that come out of these sort of traffic matrices. So Jono Took has put up a question, cross-validation. I'm not quite sure what the question is. Can you elaborate? For choice of lambda? Yeah, absolutely. So the trouble with any of these things like cross-validation, is you need ground truth data. So in the setting at AT&T, the advantage that we had was they actually could see part of their network. So if you looked at a network like this, then there'd be some chunk of it down here, which they could measure, some chunk of it down here, which they knew the traffic matrix. They had another measurement infrastructure for getting the traffic matrix. And so we could do that, and that's how we tested the accuracy and how we could find the optimum value of lambda for our network. But this is in the context for, say, an arbitrary network operator who doesn't have that. That's the whole point of this inference, is to be able to estimate a traffic matrix when you can't get to that original, that real data. So you have to be able to choose a value of lambda in the absence of being able to test it like that. You can test for sanity and do various things, but it's a little more tricky. So what else do I want to say? Firstly, any other questions? I find that with Zoom, I just have to persuade myself to be quiet for a minute to let people ask questions. So excuse me while I've got a cat here. I'm just going to pat the cat for a minute. That's not a euphemism. It's a real cat. While you think of your questions.
So Matt, it's Peter Taylor here. I've got a question.
Hey, Peter.
So I look at what you've got there, and it looks to me like a Lagrangian of a constrained optimization problem.
Absolutely, that's exactly right. In fact, you can rewrite these in duals, and you can do a whole lot of that sort of view of it. One way would be to say you want to minimize this distance subject to those constraints, and then those constraints would come in as the Lagrangian. Yeah.
And
so
then
you're exactly right.
Use that dual to choose the best lambda, not just choose any old one.
Yeah, so the optimization guys have any number of ways of turning around this and rewriting it in alternate ways to get different aspects of it. But the fundamental problem with optimizing lambda is that at some point to do that, you would need to know y and x, at least for some of those measurements. You need somewhere where you have ground truth, where you have some piece that you can cross-validate against, or such and such. So it was, for us, very important that you had a technique which was able to cope with a wide range of values of lambda. And because that's on a log scale, I mean, we could cope with lambda, I can't remember the exact range, it was like 1 to 100 would be like reasonable, and 23 was the optimal value. So it's really a good space to be in. So I have another question from Ryan Diski. Isn't that what we use to estimate the traffic matrix? That's what I'm trying to sort of say. I'm not sure I understand the question. This arg min x is the thing we're trying to estimate the traffic matrix. That's right, but you can always solve dual optimization problems and twist things around, so you're actually doing something different.
Hi, it's Ryan here. Can you hear me? Okay.
Yep. Great.
Yep. So my question is that in order to calculate this x hat, we need observations of something.
That's right.
Could we not cross-validate using those same observations to find estimates of, or to cross-validate for the value of lambda that gives us the best predictive power, not necessarily on the things that we can't see, but the things that we obviously can see because we're using them to estimate the estimate of x? Or is there something I'm misunderstanding here?
Yeah, I'm just trying to add a little bit of extra notation just to remind us. We observe the y's, the x's are not observed in the standard problem. And I just corrected a little bit of notation over here. The model is based on the measurements y, not x. As soon as you have some values of x and y, you can make that connection. But the problem is that we only observe the y in the raw problem. We only observe the y's, we never see the x's. And so you never have anything that links those two. You don't have any observed predictions, if you like. You only have predictions. So it would be like trying to do cross-validation in a space where you have this model, you predict some values, but you can never actually see whether those values were good or not. Does that answer the question at least a bit?
Yeah, a little bit. I mean, we see the values of A, is that correct? Or
we assume we know the values of A. That's actually a measurement problem in its own right, but yeah, we assume we know the values of A.
Okay.
Have a little bit more of a think about it.
Yeah, I think I need to have a bit more of a think about it. I haven't quite got my head around where everything sits here at the moment. But yeah, thank you for your answer.
I'm really happy to answer questions, and if you want to just offline send me a question afterwards, then that's welcome as well.
Mm-hmm.
I, just trying to express the fact that depending on the way you have this problem set up, you sometimes have a little extra lever you can pull, and that lets you do something like cross-validation or some other variant of these things. But in the simple original version of this, there's just there's no place where you have that lever. But as I said, the choice of lambda turns out to be really robust anyway for the certain sort of problem that we were working on. How you actually solve this optimization problem varies. And one of the other tricks to pull in here is that if you put the straightforward Kullback-Leibler divergence in here, it's a convex optimization problem. We have lots of techniques for solving convex optimization problems, but there's also some constraints here. I really should point out that x has to be greater than or equal to 0. So there are constraints in here. In addition, so we end up with a constrained convex optimization problem that could be quite painful at the scale that we want to solve. I know there are lots of good techniques for solving them, but this is a really big problem. It's also a really sparse problem, and what I mean by that is that this matrix is a sparse matrix. The incidence matrix we're working with is quite sparse. And there are optimization gurus out there who spend a lot of time working on how to solve optimization problems in the context where you have sparse objectives like this. The code that we had available would only solve quadratic optimization problems. So one of the tricks you can pull is approximating this as a quadratic. And you can do it as a weighted quadratic. You can do all sorts of clever things here, but it's just one of the tricks that is really powerful in mathematics in this sort of space, is knowing when you can approximate something, simplify it just a little bit, and suddenly you get this vastly faster machinery to do the next bit of the problem. So that's all actually really old work back from the days in AT&T. Okay, I've got a couple more questions. So let me have a look at these. Can we do PCA to reconstruct the traffic matrix? What do I want to say about PCA? Give me a second, I'll come back to that. Do typical A's have some sort of structure? Absolutely, they have a lot of structure, because they are really just a reflection of the structure in the network. So I can't very easily describe that, but let me draw a picture of a typical network. It might have these things we call pops. And then these pops are joined together in a really regular way. This would be, say, pop, point of presence 1, point of presence 2, point of presence 3. And you can actually construct networks that look like this using graph products, and we can always write graph products as a type of Kronecker product of the underlying adjacency matrices. So if you take the adjacency matrices for each of these pops and this sort of larger scale, call that this larger scale view of the network, the pop level view of the network, you can take a Kronecker, a type of graph product which corresponds to a Kronecker product of the adjacency matrices, and that will introduce this block structure into that adjacency matrix for that graph, and the structure of the adjacency matrix then determines the incidence matrix, the routing matrix for that network. So there's a great deal of structure in there. But the structure is quite complicated, and as far as I know, not very useful to me. So I don't know how to do anything with that. So, Jan, if you have some ideas, then I'd love to hear them. Getting to the PCA question. So there is a big topic these days called matrix completion. Talking about completion, we did that work 20 years ago, really. Not quite 20 years ago, 15 years ago. I've been back in Australia for 15 years or so. And I have worked on many things since then, many things. Traffic matrices have been sort of a little bit sidelined, but I still do some work on them. A few years ago, we did some work on traffic matrix completion. So let me just very quickly try and sum up what you're doing with traffic matrix completion. So we start with, again, something like this: yi equals A transpose xi. So imagine this is at time I, and this is a traffic matrix stacked as a vector. Then we can rewrite this as y equals ax for, I equals 1, 2, sometime t. Now, one of the things we can do is imagine that we have some measurements of this and some measurements of this x. So, imagine x is something like this: 3 question mark, 4 question mark, 1 question mark, 0, 3 question mark, 1, 1. So now the problem is in this category of matrix completion, where what we're trying to do is fill in those gaps in the matrix in the best way we possibly could. Again, we're going to use the same sort of regularization framework. So we're going to end up with something like x hat equals arg min x greater than or equal to 0. And we're going to have some sort of norm of difference between these two. And again, we might have some sort of regularization term. I'm not going to write down what that is at the moment because it's so problem dependent. But this time the problem is actually characteristically quite a lot different from the problem that we had before, because I know some elements here and I know some elements here, but not all of either of them. And I can imagine other situations where, in fact, I don't know this matrix A transpose X. What I actually know is some sort of measurement matrix. So I make this even more general. I know some sort of measurement matrix of X. And that could include linear combinations that arise from other than edge measurements. What can I do in this sort of context? Well, one way of trying to tackle this is to look at some sort of matrix decomposition of that matrix and try and solve for these guys. Without, while being aware I'm sort of at my time limit, without wanting to go into too much detail, a sort of generalization of PCA does this. And so PCA, we have used that sort of PCA type idea to perform this type of reconstruction. And PCA has been used in this world to do a number of other problems as well. But actually we found another technique that was a little bit better than PCA. So I think Gaussianity, while it's not necessary for PCA, it is one of the things that make PCA work particularly well. So I'm getting messages from at least one person saying they have to leave, and it's 3:30, so I need to finish up. That's really the end, unless there are any more questions. Well, let me, the cat has to say goodbye to everyone. Well, possibly not say goodbye to everyone. Have a little wave. And I'll see you later. Thank you very much.